start now?
Yeah, I can see the presentation.
Okay.
So let me start. Yeah, let's start right now. So
Okay.
next speaker is Dr. Hui. She will talk about termination of the superradiance from a binary companion.
Okay. Well, hello everyone. I'm Zhu Huiyu from Hong Kong University of Science and Technology. Today I want to present my work in collaboration with Tong Xi and Professor Wang Yi. And the topic is termination of superradiance from a binary companion. So to start with, I want to firstly introduce what is superradiance and what is gravitational atom. Superradiance or superradiant instability means that a curved black hole can grow an ultralight boson cloud around it, because the ergo region of the curved black hole can amplify the incoming wave, and the small mass of the boson field can act as a natural mirror to reflect back the outcoming wave to the ergo region and make it amplified again. So at last, there will be a cloud of boson generated by the curved black hole. And because of the gravitational effect, it will constrain around the black hole. And the cloud and the black hole itself can be together regarded as a gravitational atom. Here we define the gravitational fine structure constant alpha equals to gmb mu. And mb is black hole mass, mu is the boson mass. Because we need the small boson mass, so this alpha should be smaller than 1. To study this, to study the property of gravitational atom, we can take the Kerr metric into the Klein-Gordon equation here. And by expanding it to the leading order of alpha, we will get a Schrodinger-like equation, just like the hydrogen atom. But actually, this gravitational atom is different from the hydrogen atom, because after we solve that Schrodinger-like equation, although we will also get some eigenstate which can be labeled as an LM, but we will get different energy eigenvalue with some extra imaginary term. And this kind of imaginary term can be finally absorbed into the amplitude of the scalar field. Sorry?
Oh, sorry, no. Okay.
Okay, so this imaginary term can be finally absorbed into the amplitude of the different states. So if gamma NLM is smaller than 0, then it means the state NLM is an absorption state. And it means the cloud will be absorbed into the Kerr black hole in the rate of gamma NLM. And for the same reason, if gamma is bigger than 0, then it means the cloud, this NLM state is a superradiant state. And the cloud can be generated by the black hole with the rate gamma NLM. And here, gamma NLM has been calculated, which is proportional to alpha to the 4L plus 5. And for the real part of this energy eigenvalue, ENLM means the energy of different states, just like the hydrogen atom. So we can see there will be a Bohr splitting, fine splitting, and hyperfine structure splitting. And also the energy spectrum is presented in this figure. We can see the different NLM here. So what phenomena does gravitational atom have? Firstly, if we consider the isolated gravitational atom, we will find that the cloud, the boson cloud, will extract the black hole spin. And also the boson cloud itself will emit a monochromatic gravitational wave via pair annihilation, which can be detected. And also, if we consider a binary system, the more interesting thing will happen, that the periodically potential change caused by the binary companion will trigger the resonant transition of different states of the gravitational atom. And this phenomenon is called GCP resonance transition. That is gravitational collider physics resonance transition. And this effect can be detected by multiple channel like gravitational wave or pulsar timing array. These fields are well studied, but all this phenomena requires the cloud is stable enough and long-lived. But actually, there is some possible that the superradiance can be terminated in a very early age or a very early stage, or it can be, or even the superradiance state can be absorbed by the black hole if we introduce a binary companion inside. So we can see the Hamiltonian of the gravitational atom. If there is no perturbation of binary companion comes in, it should be diagonal, and this is energy eigenstate. But if we introduce the perturbation from the binary companion, the off-diagonal term will exist. It means that there will be overlap of different states. Now consider a situation that there is a superradiance state like 322. If it is overlapped to absorption state like 300, then it will be generated, the cloud will be generated as 322. And because of the tidal effect of the binary companion, it quickly turns into, maybe not quickly, but it turns into overlap to 300 state, and then it will absorb by the Kerr black hole. So it effectively changed the superradiance rate of the 322 state. To study this effectively change, we diagonal the new Hamiltonian here, and we will find the effective imaginary part, gamma 1 tilde equals to gamma 1 add a correction. And here, the correction is the sum of all the possible overlapping state, which is decided by the selection rules. So we can see that the correction is related to the R star, which is the binary separation between the binary companion. So we plot a figure of the effective superradiance rate and the binary separation for different kind of states. And here the solid line is for the maximal black hole spin, like the dimensional black hole spin equals to 1. And the dashed line means the black hole spin at the saturation of previous state. So the spin is less than 1. And we can see from this graph, for R star is big enough, all the gamma tilde will tend to the Detweiler result, which is the gamma, the superradiance rate without considering a binary companion. This is reasonable because when the separation is big enough, then the effect of the binary companion is negligible. But if in another way, if we consider a smaller R star, we can see the effective superradiance rate will drop to 0 quickly. It means that the superradiance can be terminated totally. So to study this effect, we define a critical distance, which means that at the critical distance, the state NLM has the effective superradiance rate 0. That is, when the R star, when the separation between the companion is below the critical distance, then the superradiance will be terminated completely. And here we plot the critical distance of different state in the different parameter space. So here alpha is the gravitational fine structure constant we defined before, which is GMB mu. And Q is the ratio of the mass of the binary companion and the black hole. So in this graph, we can see that for smaller alpha, that is a smaller mass of the boson, or bigger Q, that is the bigger ratio of the binary companion and the black hole, we will have bigger critical distance, which means the system will be more unstable because it is more possible for us to get into the critical distance. So what will happen if we consider this termination effect or absorption effect? The first consequence of the superradiance termination is that it will affect the orbital motion of the binary system. Because when the absorption or overlap happen, the cloud, the gravitational atom will change its angular momentum or lose energy or gain energy. And there will be energy exchange between the gravitational atom and the binary companion, so that it will influence the binary companion's orbital motion. We call this effect as back reaction. And this effect can be observed in multiple channels like gravitational wave detecting, or we want to introduce pulsar timing here. So in 1975, House-Taylor has used a way to detect the black hole, pulsar black hole binary orbital motion by defining a peri-astron time shift here. So they observed the peri-astron time shift change for years, and so that they use this way to calculate the period change of this binary system. So this is the peri-astron time shift for the general relativity result, which means the energy of the binary system only lose by emission of gravitational wave. But in this case, if we consider the back reaction induced by the gravitational atom, we will have an extra peri-astron time shift here. And here SC0 is the cloud angular momentum, and C1 is the occupation of the state. If the difference between this extra back reaction peri-astron time shift and the GR result is bigger than the limitation of the observation, then we can see this effect. So we use this to calculate, to plot out the parameter region of, we can successfully see this effect for different alpha and M. M here is the black hole mass. And for different observation time within 1 month to 1 century. And here we suppose the initial occupation is 10 to the minus 2. And we will have this parameter region. And if we consider a more dilute cases like 10 to the minus 6, then we cannot see it within 1 month and 1 year anymore. So the parameter region will shrink if we have more dilute cloud. Another consequence of superradiance termination is that it has an impact on the gravitational collider physics resonance. So let me review this again. Gravitational collider physics resonance means after we introduce a binary companion, if the orbital frequency match the energy difference of different states of gravitational atom, then there will be a quickly state transition between the two states. And it will also give a back reaction to the binary companion, which change the orbital motion of the binary companion. And it can also detect it by gravitational wave detecting, or also detected by the pulsar timing array. But in our case, we need that when the GCP transition happen, the separation of the binary companion should be bigger than the critical distance. All the cloud will be absorbed and there will be no resonance anymore. So in this case, we put in this constraint into the GCP transition, and we find out some safe region for different kind of transition, like hyperfine, fine, and the Bohr transition. We can see from this graph that the Bohr transition is influenced most because the energy difference for Bohr splitting is bigger. So it needs larger frequency to get into the resonance. This means the separation between the binary companions should be smaller, relatively small. So it is more possible for this binary separation smaller than the critical distance. So we will have more bond on the Bohr transition. And similarly, because the energy difference of hyperfine transition is small enough, so it is not influenced like this way. And the final consequence of superradiance termination is that it can relaxing the Boson mass bound, because nowadays we use many ways to detect the Boson mass, like LIGO search the continuous gravitational wave from the Milky Way center. And because the Boson mass cloud, the Boson cloud will emit gravitational wave by pair annihilation. So they give a bound of that. And also they can use they can detect the black hole spin to detect the boson mass, because the boson cloud will extract the black hole spin, and they can measure it in a statistical way. And also there are many other bounds, but all of these bounds assume a presence of cloud. So if the superradiance can be terminated in a very early stage, or even the superradiance state, highly superradiance state, can be absorbed by the Kerr black hole, and there is no existence of the cloud, then this kind of mass bound will be relaxing. Okay, so let's come to the conclusion. So in this talk, we state that the superradiance state can couple to many dangerous absorptive states, make the superradiance being terminated or making the cloud being absorbed. And we define the critical distance and we calculate the effective superradiance rate. And also we discussed the termination of superradiance can cause following effect. Firstly, we can observe the cloud absorption via multiple messengers like gravitational wave detection or pulsar timing array. And also it poses the tight constraint on the possible gravitational collider physics transition because of the safe region, the critical distance effect. And also this effect can relax the constraints on the ultralight boson mass. And in the future, we can consider more general orbits, because in this work, we only consider coplanar big circle orbits. And also we can study in detail how this effect will affect the boson mass bound. Okay, this is all my presentation. Thank you for listening. Is there any question?
Thank you very much. So questions? If anyone hasn't, can I ask one question?
Yes, sure.
So I little confusing for the state. So they are labeled by LMN. So this almost like the hydrogen atom you said. So did you really quantize the particles, or so this is simply labeled by some spherical harmonics of the waves?
Yeah, it's simply labeled by, it's just an analogy of the hydrogen atom.
Well, you never quantize it, just state by the label by some orbits or wave. I see. So but you only consider some kind of circular motion, not the generic motion around.
Yeah, we only consider the circular motion.
Yeah, but in that case, maybe you don't have some three different numbers like that. If you have some circular motion, then you have only one or one numbers.
Sorry, what number?
So in a shredding in a hydrogen atom, so we have three different quantum numbers because they just consider most generic kind of the motion around the atom. So you have three different numbers, L and N, right?
Yeah.
But you consider only some kind of circular motions, right?
Yeah.
In that case, you still have three numbers, L and N.
Yeah.
I don't get it actually. How the element comes.
I mean, the circular motion is for the binary companion. I mean, the binary is a circular orbit.
Yeah.
With the black hole, but not for the boson. I mean, boson cloud.
Oh, I see.
Yeah,
okay, only for the binaries. Okay.
Yeah.
Boson has a kind of arbitrary motion around it.
Yes.
Okay. Sorry. Another question from Rongan. Is that right?
Sorry.
Yeah, you have a question, Rongan, right?
No, I have
no question. Okay.
Thank you.
Yeah, we still have 4 minutes. Any other questions? Okay, can I ask one more thing?
Yeah.
So you still have some kind of concept like a Bohr radius in this case?
Do you mean the cloud radius?
Yeah, cloud, some radial limit inside that we almost have that bosons, but outside there's no bosons.
Yeah.
Can be determined by what?
I think it can be. Wait, let's check. It's just. I think it can be determined by boson mass and black hole mass.
Yeah, I understand.
Just
okay. Yeah. So Professor Jutta Kunz.
Yeah, Jutta.
Yeah, please.
This has been a very interesting talk, I must say. It's very amazing that you get rid of some of these clouds in some ways. And I was wondering, do you also, do you just consider scalar clouds, or do you also consider vector bosons? Or
in this case, we only consider scalar boson.
Because
in this work.
And there are these interesting calculations of boson stars, and there is this distinction between the scalar type of boson stars and then Kerr black holes with the scalar hair, with the Kerr black holes with polka hair, with the vectors seem to be more stable. So in that case, it would also be very interesting to know about the vectors.
Yeah. Maybe we can study it after that.
Yeah. Okay.
Okay, thanks. One more kick. We have 2 minutes. Otherwise, thanks speaker again for the nice talk. Thank you very much. So who is next speaker? Next speaker